So in this lecture, we will look at a few failures and accident investigations and see how the reliability of the turbofan engine has been improved to such an impressive extent that we see it today. Okay, so NTSB, most of the videos have NTSB investigators who look at who try to sort of reconstruct what happened and then suggest improvements, changes in procedures, inspection procedures, and things like that.
What does NTSB stand for?
National Transportation Safety Board of the US. Because most of the aircrafts are manufactured in the US, regardless of where the accident takes place. Usually, since the aircraft is manufactured in the US, NTSB representatives will always be there. There will be local air safety investigators, but NTSB investigators will always be there. Come. So whether it's a 737 accident in Ethiopia or Jakarta or wherever, NTSB or Japan, NTSB investigators will always be there. If the accident is in the US, then they will have the lead role to play, and invariably black box recorders, CVRs, and flight data recorders are invariably taken to NTSB headquarters in Washington DC, for transcription and so on. So they take the lead role in this. So let us see a few. I have put together a few things which I thought would go well with this lecture. There are many interesting investigations and videos, but let us start with the first one, which has to do with the compressor stall incident that we looked at earlier. If you remember, there was a British Airways aircraft in Phoenix, Arizona, which had a compressor stall. Compressor stall usually happens only during the takeoff roll when the engine is at maximum power setting. But in the case of the British Airways flight, since it was already moving past the decision speed, they had no option but to take off, dump fuel, and then come back, which usually will take about an hour or so. So they can come back and land only after about an hour, because it is fully fueled for the long transatlantic flight. Now in this case, the engine is shut down. The engine will be shut down. The runway also has to be inspected, as you saw, because there is always a possibility of debris from the engine having fallen on the runway, and if the debris is ingested by other aircraft, then that could cause severe damage. So the runway has to be inspected before it is cleared. Okay. In fact, one of the most famous incidents, the accident that really brought Concorde to its knees, was such an incident. The aircraft, presumably the aircraft that took off before Concorde in Charles de Gaulle, apparently had some issue, and a component actually was lying on the runway. So when the Concorde took off after that, that particular piece of debris punctured the fuel tanks and caused the fire, which eventually scrapped the Concorde program. They just could not recover from that. So that is why it is standard operating procedure. In case that there is fire and sparks, then the runway has to be closed and inspected before being opened again. Okay. Now in the case of this Indigo aircraft, last month at Delhi airport, again this Delhi to Bangalore Indigo flight experienced an engine stall similar to what we had. Fire was just pouring out of the engine. There are some videos that are available. I didn't just show that, but there are videos taken by a passenger, and but fortunately this happened before they had reached the, as I said, the V1 speed, which is the decision speed. So they were able to decelerate the aircraft, stop it, and then takeoff was rejected, and the aircraft came back to the bay. But the most important thing is, when we say the takeoff was aborted, that means the engine has to be, the aircraft has to be brought to a complete stop, which means there is a lot of pressure on the brakes to bring the aircraft to a halt. Normally, during such episodes, you do not use the thrust reverser. The brakes in the main landing gear are used for bringing the aircraft to a halt. Okay. So as with any other component, the most important rule indeed for aircraft companies, indeed for mechanical engineers, is hope for the best, plan for the worst. Yeah, I think A320, I think, if I am not mistaken. Yeah. but stall can happen in any of the engines, but largely, I mean, to a large extent, it depends on many things that the pilots do, but it also depends on the ambient conditions, to a large extent. So, okay, so let us see how they actually test the brakes, for aircraft like this. What would you do? What is the worst case scenario, right? So, in this case, we are actually seeing a rejected takeoff brake test for a Boeing 747. It is fully loaded, maximum takeoff weight, with the brakes having the minimum lining. There is practically no lining material in the aircraft.
The new Boeing 747-8 is a massive machine, designed to take off at close to 1 million pounds. Through months of flight testing, the airplane has shown plenty of power on takeoff. But how would it handle all that energy if it had to suddenly stop?
In the emergency event that we have to make a rejected takeoff at these heavy weights, it takes a long distance for the airplane to stop. It's just like in your car.
Captain Kurt Vining and the Boeing Test and Evaluation team are about to put the airplane through the ultimate rejected takeoff, or RTO. First, the crew installs a set of 100% worn-out brakes.
So it's down to the stud. So if you've ever had your own brakes, they've got a machine down, so there's just basically no material left.
Technicians also fuel the airplane up to maximum takeoff weight of just over 975,000 pounds. At the start of the runway, Captain Vining begins the takeoff roll as usual, pushing all 4 engines to maximum thrust. But just as the airplane is going at over 200 miles or 320 kilometers per hour, he slams on the brakes. To channel maximum energy to the carbon brakes, the pilot cannot use the thrust reversers.
The whole intent is to demonstrate under the worst conditions, you could safely stop the aircraft.
The brakes, made by Goodrich, do exactly as they're supposed to. In fact, the 747-8 stops earlier than the team had hoped, beating the target by more than 700 feet or 200 meters. But stopping is just half the challenge. Now the airplane must prove it can withstand the tremendous heat that built up in the wheels, estimated to be more than 1,400 degrees Celsius.
And it's a simple physics problem. We have to turn that kinetic energy into heat in the brakes.
As expected, smoke pours out from the brakes as they glow a bright orange. Still, the firefighters who are standing by can't do anything but watch for the next 5 minutes.
And that's to simulate that if you were at an airport, you had an RTO, you wouldn't necessarily have the fire department right there. So you demonstrate that worst case would be 5-minute response time for a fire department to get to the airplane.
By design, special fuse plugs in the tires are activated, deflating the tires before they explode. Finally, at the 5-minute...
This is also the reason why aircraft tires are inflated with nitrogen and not with air, so that there is no oxygen in the vicinity of the carbon brakes, which usually are at very high temperatures when the plane comes into land. But generally when the plane lands, after the plane lands, but when the plane lands, of course, in the normal circumstances, you would be using the thrust reverser to decelerate the plane. Much of the work is done by the thrust reverser, so the brakes are not working as much. But this is, as we said, the worst case scenario design, that it should stop even under these circumstances.
Mark, firefighters move in with plenty of water. While the tires and brakes will have to be replaced, the rest of the airplane is perfectly fine. No sweat, even for the flight test engineers who were on board.
It went amazing. The decel rate was exactly what we expected. Great stopping, no major faults.
Slamming on the brakes so the new 747-8 can continue moving towards certification and delivery.
Yeah, it is made out of carbon fiber actually. Metallic would not work, so this is this carbon composites on the brake. Okay, so the basically the point or the takeaway from the previous video is, we may say the aircraft had a compressor stall and then it was safely returned to the gate or the bay. There is a lot that goes in, because you have to do all this and the engine has to be certified. It could be raining, tarmac could be wet, there are all sorts of difficulties in the actual service condition for these aircraft. The next incident that I am going to show was in a Southwest flight from LaGuardia to Dallas Fort Worth, and it was a Boeing 737, And when it was cruising at 37,000 feet, one of the fan blades came out. So it had what is called an FBO, fan blade off event, and the fan blade came out. Apparently the fan blade was contained, but there was a lot of debris as a result of the fan blade ejection, and some of the debris made it out of the engine, impacted the wings, impacted the engine spar, and one of the debris happened to impact a window that was located above the wings. It was just above the wings, and the window was shattered, and the plane immediately underwent a decompression because it's at 37,000 feet. And a passenger unfortunately was pulled out, but others managed to pull her back in, but she eventually, she died, so that was very unfortunate. So under these circumstances, whenever there is a depressurization, because oxygen masks come down, and the first priority is to bring the flight back to an altitude of 10,000 feet or so, because at 10,000 feet you can breathe easily with there is sufficient oxygen in the air, so that is the first priority. So you have a very rapid descent to 10,000, and then you respond to whatever emergency that you may have. I am going to play a recording of the conversation between the pilot and the ATC when this incident happened. And what is remarkable about this exchange is the manner in which the pilot, she was a Navy fighter pilot, the manner in which the pilot communicates with the ATC. I do not think too many people in the world would have actually managed to communicate with the ATC like this after an incident like this. Okay, let's take a listen.
Southwest 1380 has an engine fire descending.
Southwest 1380, you're descending right now?
Yes, sir. We're single engine descending. Have a fire number 1.
Alright, Southwest 1380, okay, where would you like to go to? Which airport?
We're looking at Philly.
Southwest 1380. I understand your emergency. Let me know when you want to go in.
Yeah, we have a part of the aircraft missing, so we're going to need to slow down a bit.
Southwest 1380. Speed is your discretion. Maintain at any altitude above 3,000 feet, and you let me know when you want to turn base.
All right. Down to 3,000. Southwest 1380. Like to turn.
Look at the damage on the wings.
Southwest
Here,
1380, turn,
and here.
start turning southbound there. There's a Southwest
Throughout the leading edge.
on a 4-mile final will be turning southbound. Start looking for the airport. It's off to your right and slightly behind you there. And altitude is your discretion. Use caution for the downtown area. Advise you maintain at above 2,200 for the MPA.
Okay, could you have the medical meet us there on the runway as well? We've got injured passengers.
Injured passengers, okay. And is your airplane physically on fire?
No, it's not on fire, but part of it's missing. They said there was a hole and someone went out.
I'm sorry, you said there was a hole and somebody went out? Southwest 1380.
So this is incredible, So the air traffic controller says this and then realizes, okay, it doesn't matter. You just get down, then we will take a look, It's just incredible. The manner, the calm tone, she's not at all perturbed, everything is under control. She has nerves of steel, as one of the passengers described. There is actually there is another video in CBS News. I didn't want to show that because it shows the picture of the victim. It was just for me too graphic to show. That's why I chose not to show that and show this.
Doesn't matter. We'll work it out there. So the airport's just off to your right. Report it in sight, please.
South 1380, airport's in sight.
Southwest 1380, runway 27 left, clear to land. Southwest 1380, right turn when you're able. If you want to stop wherever you need to is fine.
Thank you. We're going to stop right here by the fire truck. Thanks, guys, for the help.
So you can see, the other incredible thing about this is the manner in which the pilot landed the airplane with just one engine. The other one is completely destroyed. So she managed to land the plane without any issues with just one engine. It goes to show how incredibly trained these pilots are. So what you do is you fly with full rudder to the other side. Not flaps, rudder. So the rudder is in the tail. So you adjust the rudder. So the rudder is in the. So you look at the vertical stabilizer. Part of that is the rudder. So when the rudder goes to, so let's say this is the flight. When the rudder goes this way, the force on the rudder is like this. So it will yaw this way. When the rudder goes this way, the force on the aircraft is like this, and the aircraft yaws this way. So when you have one engine not producing thrust, it has a tendency to yaw, like you said. So you use the rudder, full rudder, the other way to actually control the yaw, and you can still fly the aircraft. It will be very difficult because you have to hold the rudder in that position continuously, which is very difficult, but it will be, yeah, it will be, but there have been other instances when that has happened, and in fact other videos that I show also have the same problem. When you lose an engine, it always has a tendency to yaw. So with the full rudder control, pilots have managed to land the flight. It is very challenging. It is not as easy as it looks, far from it. These professionals make it look very easy. That is the thing.
Does the pilot actually come to know that the engine has failed through some electronic?
Definitely once this happens, you will get warnings from the from the console. You will notice that the engine RPM is not steady. You get lots of lots of indications on the console. Not exactly what happened will not be known at that time. So she initially thought it was on fire. Then later on, see, once the decompression happens, the first thing is to bring it down, because the oxygen for the passengers will last about 15-20 minutes or so, no more than that. So the first priority is to descend rapidly to 10,000 feet and then take stock and respond to whatever emergency you have. In fact, the normal cabin altitude pressure itself is only about 9,000 feet or so. It is not maintained at sea level pressure. That would be too much. So they normally maintain it at about 9,000 feet or so. Well, 9,000 feet normally. I think the 787, they can maintain at 8,000 feet or so. That is what they do. They don't prefer to maintain sea level, because that means taking more air from the engine. So the engine for cabin pressurization has to be taken from, the air for the cabin pressurization has to be taken from the engine. And so as you take more air, yesterday we talked about cooling the blades, taking bleed air, now if you take more air, that means your fuel economy goes down. So they try to maintain it at about 9,000 feet equivalent or so. That is the cabin pressure. So here is what the engine looked like after landing. You can see the the damage to the engine, the damage to the engine spar, and the damage to all the damage to the leading edge of the port side wing. And if you take a close-up view, you can actually see one of the fan blades missing right here. Okay, so this has about 24 fan blades, and one of the fan blades is actually missing, as you can see. In fact, the fan blade containment, which is the Kevlar containment, was actually intact. But what normally happens, or what you cannot really plan for, is you carry out all the tests. We saw the fan blade off test yesterday. That is a certification test. So if you pass the test, that means you are certified to fly. But these tests, although they keep on refining the test based on accidents and other things, you cannot really conceive a perfect test which will take into account all possible service complications. So here is one such test where the blade or the debris came off and then came out through the front and then went above the engine, and the debris ricochets off the leading edge, the engine spar, and then one of it manages to go into the fuselage. That is the ultimate thing. It should not pierce the fuselage. That is the ultimate requirement. But there will be lessons learned from this, and then you work on that and then go from there. So you can see the containment shield, which is fully intact. So this is the containment shield. So the containment shield did its job, but the blade or the debris that comes off then came out, ricocheted off this part and then went out, and because the plane is moving forward, it just came back like this and hit the fuselage and so on. So eventually this engine, someone I think asked the other day about how many years these engines can be used. Typically about 10 to 20 years they are used. So this particular accident was caused by a low cycle fatigue crack which came in the root part of the blade. Remember, we saw the Christmas tree kind of a thing which goes into the hub. So this originated at the crack originated there and remained undetected for 6 years in service. These are extremely difficult to inspect and detect, but anyway, as a result of this, changes will be made to to the testing schedule and so on. So Krishnan Balasubramaniam and Prabhu Rajagopal will be very happy. More ND tests to be done, more sophisticated, more online tests to be done, so in fact, every time something like this happens and the accident report comes out and it blames cracks and crack detection, I usually send it to them, just to make them happy. The next incident that we are going to look at involves an Air France Airbus 380 which was on a long haul flight from Charles de Gaulle, Paris to Los Angeles in 2017. Okay, so this was again at a flight level of 37,000 feet over Greenland. So what you see here is actually Greenland when it had an engine failure. Remember, the Airbus A380 has 4 engines. So the starboard outboard engine, which means engine number 4, actually failed. It had again a fan blade out event, and so the pilot had a choice. There was an airport nearby in Greenland. Okay, it was flying over Greenland at the time. He could have diverted to the airport in Greenland, but it was not clear, and probably he was relatively convinced that the A380 cannot be landed in the Greenland airport. The runway simply probably was not long enough. So for that reason, the pilot, believe it or not, this is well within the safety protocols, decided to cross the Atlantic and land in Goose Bay Airport with 3 engines. Rather than land in Greenland, I said we will proceed, cross the Atlantic Ocean and then land in Goose Bay Airport, Canada. So this is Goose Bay Airport, Canada, because that had a runway which could handle the A380. So it flew across the Atlantic from here. That was where the the engine failure happened. So it flew across the Atlantic and landed in Goose Bay, and this was what the engine looked like. You can see here the entire the fan casing is completely shattered. So this was the outboard engine on the right side of the aircraft, and so the engine obviously would be shut down, but even after shutting down, this would not be a very pleasant flight because the blades in the engine, because it's moving forward at such high speed, the blades would still windmill, and because the shaft is no longer balanced perfectly as it was, passengers would feel like they are sitting inside a washing machine during the spin cycle. And that is exactly how it feels, I am told. Okay, so so it's not a very pleasant thing, but this was contained, and then the flight landed in Goose Bay Airport. But quite interestingly, subsequent investigation showed that there was actually no crack at all in the disc. So there were no cracks that were detected in the areas that were considered at risk on the fan hubs. But what was eventually found out was that it suffered from what is called a cold dwell fatigue phenomenon, and investigators then had to figure out how to account for this, how to check for this in aircraft engines after this. So normally you would expect a crack, and the crack grows, things like that. But in this case, that was not the case. And to be honest with you, I really don't know what cold dwell fatigue is. Okay, but based on the report, I understood that this is relatively new, and so now airlines and the aircraft engine companies have to start looking at this and figure out how to test for this in the future. Of course, remember this was in 2017. Any questions? The engine will be shut down, but basically you have blades, right, and you are flying in air with a considerable speed. close to 1000 kilometers an hour. So when you are doing that, the blade is like a windmill, when the wind blows, the windmill turns. So this will continue to turn and it will be wobbling because it is no longer balanced. So it will wobble, and that wobble will translate to the airframe. In fact, Professor Chandramouli of our department, he did this kind of work for Rolls-Royce. What happens in the case of a fan blade event, what would be the frequency of the wobble, and so on and so forth. In fact, a similar incident happened for, I think, a Qantas flight which was flying from, I think, Singapore to Perth or something like that. The same thing happened at 38,000 feet, and there was a passenger video which was uploaded into YouTube, showing the plane going like this. I sent that video to Professor Chandramouli, thinking that perhaps he could determine the frequency from the video, and he did, and he said that yeah, it matches with what we generally predict the frequency to be, which was quite interesting. Okay, so the next incident that we are going to look at happened way back in 1989, and this involves DC-10. So this was I think a flight from Denver, Colorado to New York, if I remember correctly. And when they were flying over Iowa, there was an incident with the number 2 engine, which is the engine in the tail of the aircraft. Okay, so I have put together small segments of video just highlighting the accident and how investigators eventually figured out what the root cause was. Okay, so the video in that sense would be somewhat sort of discontinuous, but I think you should be able to follow.
A DC-10 en route to Chicago. It's packed with children and vacationers. 1 hour into the flight, an engine fails. Although it still has 2 good engines, the plane becomes almost unflyable. 285 passengers face an horrific crash landing at Sioux City. Why did a simple engine failure lead to a crash?
I don't know, I actually saw this, the crash that they are showing happened in Sioux City, Iowa, and I actually watched this live. I was a graduate student in the US at that time. It's famously called the Sioux City crash. So this came in the news, and it was a horrific accident. Unfortunately, I think about 100 plus people, I think, perished in this accident, but the pilots were really courageous in bringing in landing the flight. Let us see.
Now you.
Was it?
A DC-10 en route to Chicago. It's packed with children and vacationers. 1 hour into the flight, an engine fails. Although it still has 2 good engines, the plane becomes almost unflyable. 285 passengers face an horrific crash landing at Sioux City. Why did a simple engine failure lead to a crash? Now you.
Okay, so we will find out next.
The bizarre loss of controls they reported during the flight.
Now we've lost all hydraulic pressure.
Captain Haynes and the crew confirmed that shortly after the dramatic failure of their number 2 engine, all their hydraulic systems went down. It mystifies investigator Frank Hildrup.
I know personally I wasn't prepared for dealing with an airplane crash where it had lost all of its hydraulics. Extremely unique event and something I personally had never encountered before.
Hydraulics operate all the flight controls on the DC-10. The flaps that...
So the flaps are in the front, as you can see, the orange surfaces. These are the flaps.
help control descent. The elevators that pitch the plane up and down. The rudder that steers it by. The ailerons.
Where did it go?
Ailerons that make it bank. Pressurized fluid inside hydraulic lines operates these mechanical controls. The rudder that steers it. The ailerons that make the flaps that help control descent. The elevators that pitch the plane up and down.
Why is it doing this? I wanted to stop and then play, okay.
The rudder that steers, the flaps that help control
So
descent.
that's one answer to your question. The rudder is in the tail.
That pitch the plane up and down.
So this is the rudder
that steers it, the ailerons that make it bank. Pressurized fluid inside hydraulic lines operates these mechanical controls. There are 3 separate and independent hydraulic systems. Even if one system is breached, it should not cause the loss of hydraulic fluid in the others. To lose fluid from all 3 systems at once is almost impossible. Experts put the odds at 1 billion to 1.
So these kind, you cannot, even a mechanical engineer will not be able to design for these kinds of odds, But today, or at least few years back, we have moved away from hydraulically operated controls to now fully electrically operated controls. Now all these controls are through electric motors, which are of course much more reliable. You can do many things, but that has brought with it its own set of problems. We need to have batteries, in the aircraft to operate all this. And of course with the lithium-ion batteries, that there is always a danger for fire, which was what the Boeing 787 encountered when it was launched. There was a huge battery fire, so then they had to design something. The battery fire problem was never solved, but the battery fire problem was contained. So they simply put a batteries in a fire resistant enclosure, so that it is fully vented and there will be no fire during flight. But now all the controls are electrically operated, but this was the time when flight controls were operated by hydraulics. Next
catastrophic event inside the engine, which then damages the hydraulic systems. They go back to the wrecked plane and examine every millimeter of its hydraulic lines. It's a painstaking process, but it pays off. They find puncture holes in the pressure lines of the plane's other 2 hydraulic systems, and the holes in both sets of pressure lines are near the failed engine.
We determined that all the 3 hydraulic systems had been breached, and that's why the hydraulic fluid was lost, and they lost the ability to really control the airplane.
It's incredible, but true. Something did put all 3 hydraulic systems out of action at exactly the same moment. But the team still has to prove that the number 2 engine caused the damage. They inspect the puncture holes with a scanning
So as you could see from that video, the hydraulic lines are not placed close together. So there are 3 hydraulic lines, and they are placed farther apart, so that in case one is damaged, you will still have 2 other serviceable hydraulic lines. So they are placed as far apart as possible, so that even in the case of a failure of one or more than one, you will still have one of the other lines left. So this was truly a freak accident, in that all 3 lines were damaged at the same time. Now after this accident there were improvements, so they redesigned the hydraulic lines, so that in case a fluid drain is detected, automatically the fluid would be stopped, the reservoir would be closed, so that you do not lose all the fluid. So there are many things that were built in after this, but you can only design for so much.
Microscope and find minute traces of titanium. Titanium is used for critical airplane parts because it's tough yet very light. On the DC-10, the only titanium anywhere near the tail section is inside the number 2 engine. And when NTSB engineers reconstruct the DC-10's number 2 engine, a new clue confirms the team's theory.
We learned that a major portion of the number 2 engine in the tail of the airplane had come apart and was missing.
The missing part is the fan disc, the massive central hub of the engine's fan assembly. It's made of titanium.
So basically, the reconstruction started with the damaged hydraulic pipes in the aircraft, and then you look at the damaged site through an electron microscope, detect titanium, then logically you infer that the only titanium that is there anywhere near this line is in the fan hub. But the fan hub is missing because it had fallen off somewhere else. The fan hub had not been located, but that is the theory.
Caused the bizarre loss of controls aboard flight UA-232. 44 minutes from disaster. The loud bang that crew and passengers hear is the 170-kilogram fan disc fracturing. The broken fan disc bursts through the engine housing. The blast fractures a section of the number 2 hydraulic system. But in a piece of catastrophic bad luck, fragments also puncture lines in both remaining systems.
1, 0 on all 3. I'm sure gauges say 0. All hydraulic quantity down.
42 minutes to go. The plane loses all its flight controls. The tail section is so badly damaged that the plane...
You could also notice that in those days, in the 80s, there were 3 crew inside the cabin. So there used to be a pilot, there used to be a first officer, and then a flight engineer who would, monitor all the instruments, and make sure that everything was working fine. So of course the role of the flight engineer was replaced by the flight computer. So now the computer does all the monitoring. So that role is eliminated now. It has its own inbuilt detection, advice and so on. So still the fan disc is missing. Once you have the fan disc, then the analysis can be confirmed, or at least the hypothesis can be confirmed.
Harvest time comes around. Janice and Dale Sorensen have a 180-hectare farm right in the middle of the search area. Tuesday, October 10th, 1989, and Janice Sorensen is out bringing in the corn.
As I was combining, I felt a little resistance on the front of the combine, and I backed it up and then put it in neutral and got out and looked, and I knew immediately that this was the piece they were looking for.
It's a massive chunk of debris, half buried in the earth. Teams from General Electric and the NTSB race to the Sorensen farm. Dale and Janice help investigators dig out the piece of wreckage. This is the Sorensens' own video footage of their find.
I had a little shovel long, and I went and got the tractor with a loader and put a chain around it and hoisted it up. And then we took it down to the turkey shed, which was not very far away. And we had hot water there, so we washed it off, so it was spick and span.
Investigators quickly confirm that the debris is a major chunk of the missing fan disc from flight UA-232. Then they find another piece nearby. Together, the 2 parts complete the entire missing fan disc. Janice Sorensen learns that her find could hold the key to the disaster.
I was very emotional about it. I had some tears. It was a combination of excitement of finding the piece and of the tears for those who'd lost their lives.
One more.
Janice and her husband Dale collect General Electric's $120,000 reward.
It was in 1980s.
They give over half the money to charity. The NTSB can now begin the next phase of their investigation. They fly the fractured fan disc to the labs of the engine manufacturer General Electric to find out what could break apart such a robust metal component. Jim Wildy, a metallurgist by training, examines the fan disc, starting with the main fracture line where it broke apart. He spots something branching off it, a fatigue crack 13 millimeters long. It's rare to find metal fatigue in a fan disc. These components are specifically designed to withstand the enormous rotational forces within the engine. Then, at the base of the fatigue crack, Wildy sees a tiny cavity.
The size of it was maximum in any one direction was about 50 thousandths of an inch.
As he scans the cavity more closely, he sees that the metal around it looks discolored. He takes a sample from this suspect area for testing. What he discovers will shock the investigation team and rock the aviation industry to its core. Investigator Jim Wildey examines a tiny cavity in the fractured fan disc from flight UA-232. What he finds stuns him. Around the cavity, there is an impurity in the titanium alloy. It's called a hard alpha inclusion, a brittle defect smaller than a fingernail. Analysis reveals that it was caused by excess nitrogen during the forging of the metal ingot. The fan disc in the DC-10 was made from titanium that harbored a fatal hidden defect. It's the final piece of the puzzle. The NTSB team can now put together the chain of events that left the passengers and crew of flight UA-232 seconds from disaster. As the DC-10's fan disc rotates at 3,800 RPM, the huge stresses initiate a minute crack in the defect. With every flight, it grows fractionally bigger. July 19th, 1989, 44 minutes from disaster. The fan disc has been in service for 15,503 flights over 17 years.
So that's the answer to your question, Parag. That engine has been in service for 17 years. Typically it would be 20-25 years or so. Inspections have, there is a schedule for that. So in this case it's quite possible that this kind of inspection was not there in the schedule. So as these things happen, the inspection schedules are changed. How frequently you must carry out this kind of an inspection on the wing, and then how frequently must it be taken down from the wing and inspected. So the schedules are there, and these are changed constantly as and when information comes.
The crack reaches 13 millimeters in length.
After 17 years.
The fan disc can no longer cope with the stresses imposed by its rotation. It shears in two. The damage it causes makes the DC-10 virtually unflyable. For the next 40 minutes, the pilots struggle to control the plane.
So that was an accident with United Airlines. That's a DC-10 in 1989. Any questions before we move on to the next one? Yeah, you could have easily flown the plane with two engines. That would not have been a problem. If they had full controls of the surfaces of the, they had full flight controls, they could have easily landed the plane. One, as you saw from that A380 video, it could safely fly with the three engines. There are no issues. This could also have flown with two engines, no issues. Well, more than that, all three hydraulic lines, being compromised at the same time was what brought the plane down. That actually, as they said, is 1 in a billion. You can't really engineer for that. So. Yeah, airlines, I don't know. I think it would have been a chain of things, engine company's liability, the airline's liability, it would have gone down there. So the lawyers would have taken over, as they always do, So, I think there is a quotation from Shakespeare, the first thing we do when we take over, we kill all the lawyers, that's what they say. So the lawyers will take over, after death, so that is what they do. Now this incident happened with an American Airlines at O'Hare during the takeoff roll. This was a turbine blade fracture, disc fracture. So what we saw earlier was a fan blade disc fracture, or what we saw before were all fan disc or fan blade fractures. Now we look at a turbine disc fracture, high pressure turbine disc fracture. So this is what the aircraft, this is what it looked like after the accident. Okay, after the takeoff roll was stopped, there was a fire, and you can see the wing unbelievably drooping down like this. The right engine had a major fire. Again, this was fully loaded with fuel for a long flight. So, but they managed to stop the aircraft on the runway itself, but the damage was huge, and there was a big fire on the in the aircraft. But fortunately and surprisingly, there are no casualties in this accident also. Okay. So there are no, we'll see this. So you can see fire in the right side engine. So the smaller piece pierced the fuel tank and then landed almost a kilometer away in a UPS facility, almost a kilometer. That was how much kinetic energy it had. So again, this engine was also had also been in service for more than 15 years. So this was the high pressure turbine, second disc. If you recall, the last lecture, we discussed which part of the engine was the most vulnerable. And if you recall, I said that high pressure turbine is the most vulnerable because it faces the highest pressure, highest temperature, highest rotational speed, and you see evidence of that here. So you can see the small fragment here, and where it ruptured the aircraft. So this is the engine, this is the spar, so it came out like that. So again, subsurface crack was most likely not detectable, but more frequent inspections of these engines were then required by the manufacturer. So that was the reason. If you look at these accidents, the reason why I said that it all comes down to manufacturing is because of lessons learned from this. Okay. So impurities in the titanium alloy. How can you have impurities in the titanium alloy? Remember, this is one impurity which is less than 50 thousandths of an inch in diameter. And these titanium blocks, are vacuum degassed at least 3 or 4 times. They are melted down in a vacuum furnace so that all the gases will escape and there will be no nitrogen bubble or no other bubbles. So, and then you actually start forging the product. And even after all this, you get these sorts of cracks or other things which are extremely difficult to detect, but still, this increases the inspection of the engine, the frequency of inspection of the engines, and so on. So the last one accident that we will look at is closer to home, and this was an Emirates flight from Trivandrum to Dubai International in 2016. It's a Boeing 777, and you see the plane here in the foreground, or what is left of it. And there isn't very much left of the plane, as you can see from here. So this actually had a fire during landing. Basically, what had happened was it was a very hot day and there was a wind shear. Okay, so basically wind shear is a very difficult phenomenon. It occurs near the ground and it is very difficult to detect. They have Doppler radars which can detect, but it is very difficult to sort of localize. So the wind shear is basically a phenomenon where the air comes down like this and then goes like this. So, when an aircraft enters the wind shear, it has headwinds, which means that pilots detecting the headwinds, they reduce the speed because there is already a headwind which increases the lift. So, they reduce the airspeed so that you can maintain the altitude as you come down. But when the aircraft passes the central core and then enters a region where the air is moving away, so that is a tailwind region, the lift drops suddenly. So, you have already reduced the speed and the lift drops suddenly, so there is no way you can control the altitude. You typically you will end up with an accident because you are so close to the ground. So, basically in this case the wind shear was detected and then the pilot aborted the landing. So, they basically wanted to have a go around and then come back and try to land again. But it was too late, they just could not spool up the engine fast enough to execute a go around. By the time the landing gear had already touched the ground, at which point the auto throttle and the autopilot disengages the engine. So, their command to increase the thrust it took a while before that could be executed. So, that it resulted in a major fire. There were about 300 souls on board, including flight crew and passengers. Okay. Can you guess how many fatalities there were?
0. I hope so.
Why 0? After this, after seeing this, how can you say 0? That is actually the reason. So, even in the previous incident, there were no fatalities because the evacuation procedures are so efficient. So, you can evacuate a Boeing 777 like this in less than 2 minutes, because that is all the time you are going to have in case of a fire like this. So, all the passengers were evacuated. But still it was very tragic because many of the passengers were from Kerala and they are all migrant laborers in in the Gulf, and they lost many valuable documents. They lost their passports, they lost their work permits, so it was a very tragic accident for them. But not only that, many of them suffered a lot of sort of burn injuries because they had to escape out of the chute onto the runway, and because it was it was so hot, the outside air was at about 50 degrees Celsius or so, and the tarmac was even hotter. So, most of them had burnt feet from standing on the tarmac or running across the tarmac. It was a very difficult accident. I think the first one where for Emirates, I think where they were not able to recover the flight, where they lost the aircraft completely. Okay. But again, in this case, as you rightly pointed out, the evacuation is so efficient that they were able to evacuate the flight in less than 2 minutes. 300 passengers or 300 souls, they could evacuate. So, it was quite impressive. Any questions? It is completely destroyed because I think the landing was very hard. They wanted to abort the landing, but it had already landed. It slammed into the ground, and with the fuel that is left, definitely a fire is unavoidable. Fire is still probably the most challenging safety aspect of aircraft. I think many other things have been ironed out. Loss of lives when you have a fire still is something I think we have to get over. So, because there have been incidents, so you see the escape chutes, things like that. But there have been incidents when one of the debris from the fire punctures the air sacs in the chutes, and the chute is useless. One less chute means you cannot evacuate people fast. So there are still a lot of challenges for in this kind of design. In fact, if you look at the chute itself is actually a marvel in engineering. It inflates in, if I remember correctly, less than a second, I think. From being stored to being fully inflated, it takes less than a second, and that is a gas dynamics problem. It's an extremely interesting mechanism that they use to inflate these chutes. It's It's quite interesting. So the basic takeaway from all this is that that improvements like this, which increase the reliability, and improvements which increase the fuel economy, are what made the ultra long haul flights possible today. That was what we started with, and these are the things that make it possible. Now we will see the next lecture, we will see what latest things are on offer in the aircraft industry as of today, or what is coming up, what is on the horizon, what improvements have been done inside the engine. So we will look at that. That is tomorrow, right? Tomorrow? Okay. So we will finish tomorrow. Any questions from the students? Go ahead.
So in the case of a crash, is the runway the best place to land? Because I would think that any soft kind of ground would be less.
No, if you happen to go on the on the shoulders or off of the runway, then usually it's very difficult to control the aircraft. It will definitely plow into the field, and it may cause more damage, because if it lands on the runway, there is a possibility that you can still evacuate people. Fire trucks can get to you, so that is always the safest option. You can still manage to sort of come down on the runway. There have been incidents when planes have landed, done a belly landing on the aircraft, and people have managed to survive. So that is still the best option. But what you would need, many Western airports have this. They also have additional regions beyond the runway, on both ends of the runway, to prevent aircraft from going over the runway. They have many additional things, which things like that would have prevented the Calicut or the Kozhikode crash, for the Air India Express. So that is a tabletop runway, extremely difficult to land. So additional things like that, if there is room, those would actually help. But runways, I mean airports, airlines, they are always under the squeeze, of profit margins and so on, so, but they will comply with most that is required, so, but that is the answer to your question. Being on the runway is probably the best thing. Being off, the Iowa crash, the aircraft actually ended up on the side of the runway in the field. They still managed to evacuate, but then you have completely lost control when it goes at such high speed over mud or soft ground. That's actually worse, in fact. There have been incidents, in both engines failing. You saw, in the Hudson River miracle. That's a Captain Sully story. There is a so that has happened. Both engines failed due to during takeoff. Due to bird hit on both the engines. That has happened. There is also there are a couple of incidents. One, I think Air Canada, which lost all its engines, not due to an accident, but believe it or not, due to a conversion mistake. That was the time when Canada, I think, was moving over to Canada, UK. They were all moving over to the metric system from the British system. So someone forgot to divide the amount or multiply the amount of fuel required by that factor of 2 in going from pounds to kg, and it had only half the fuel that it is supposed to have. So they basically ran out of fuel over the Atlantic Ocean. And fortunately, for the passengers, the captain happened to be an expert glider pilot also. So he actually managed to bring in a twin aisle wide body airliner safely down on the runway without any casualties. This is normally when this happens, once the CVR is recovered, once the flight data recorder is recovered, so these things are normally then put into the flight simulators for pilots to train against, these kinds of emergencies. I believe to this day, no one has been able to land the plane in that incident. A simple conversion, multiplying by a factor of 2. And then there was also an incident of British Airways Boeing 747 flying I think from Singapore to Sydney, I think Sydney or Perth, Australia. I think while they were cruising, there were mysterious things, they were seeing some mysterious sort of like, the northern lights, aurora lights, they were seeing that very unusual, because they were flying over the tropics, near the equator. So they were seeing all kinds of things, and one after one, all the 4 engines shut down. All 4 engines shut down, So then they managed to actually, they were flying over Indonesia at that time, and the pilots actually managed to bring the aircraft back and safely land in Singapore. Eventually, it was determined that as they were flying at about 37,000 feet, basically they actually flew into an active volcano. There was a volcano which was spewing out debris. They just did not know, and they just flew through the volcanic ash cloud, and the ash cloud basically just gummed up the entire engines. So if you throw mud into the engines, what do you expect? So all 4 engines shut down, but they managed to land the flight. So yeah, I mean, yeah, but you don't plan for these kinds of things, so you cannot really attribute 0 casualties. In this case, to the engine manufacturers or the aircraft manufacturers, you have to attribute it to the pilot skill. No doubt about that. So running out of fuel in a big aircraft has happened in a couple of instances. One was this Air Canada incident, and then there was also another incident, I think, in which that had happened. Again, they managed to land the plane with 0 casualties. That sort of thing will not happen today, though. I think they have much more sophisticated ways to make sure that you are fully fueled, before you take off. Yeah. Now they have much more sophisticated ways of doing this. They still have to enter the takeoff weight, in the flight computer, but that is baggage, and other things. They would know the amount of fuel that has been loaded, and now these kinds of things, there will be standard operating procedures for all these kinds of things nowadays.
Currently, are there any regulations on what is the maximum number of years an engine can be? Because we saw most of the failures are from fatigue cracks.
No, as long as I said, as long as you go through the proper protocols, and the servicing requirements for the engine. Engines can be in service for 20-25 years, and they are actually in service for 20-25 years. They are terribly expensive. What happens is after a long time, it's very difficult to get genuine spares for these engines. That is what becomes a problem. After 25 years, it's very difficult to get genuine spares, for engines. So, and you cannot really put cannibalized parts, from other this thing into this. But the good thing is, many of the really old aircraft and old engines, probably are being used in freight, for the freight aircraft. So, yeah, it's okay. Yeah, but even airline companies, still they would try to use the engine to the max possible, and engines are much better instrumented nowadays. As you saw from that Rolls-Royce video that I showed, there's a lot of instrumentation that goes into an engine. All this data is collected actively and communicated through Inmarsat, to the engine manufacturer. So they run all this big data analytics, all these things. So the hope is that they can detect some problem even before you notice the problem. That is the general idea, so they can tell the airlines in advance that this engine needs to be inspected, and things like that. So we have come a long way, in doing that.
Very early accidents in the 50s and so on, seem to be airframe failures. That is now eliminated.
Yeah, we did have airframe failures, but there are many lessons learned, from the pressurization and depressurization. That is by and large eliminated now. You don't really see airframe failures now. Although Boeing 787, I think because it's made out of composites, they are seeing some new trends, but still safety is not compromised. So the way I think composite will respond to fatigue loading is understandably different from the way an aluminum skin would respond to fatigue loading. But I think it's very rare to see. In fact, I have not seen an accident involving airframe failure in recent times.